All right, hello everyone. It's just gone past the hour, so welcome to the 0100 UTC session of Science of Low Frequencies 7. This is the first of 3 Epoch of Reionisation and Cosmic Dawn sessions that we will have as we go all the way around the globe to hear about all the great EOR and Cosmic Dawn science. So if this is the first time you've logged into Science of Low Frequencies, this is a Zoom webinar, which means that unless you are presenting, you can't unmute and you can't turn your video on. If you do have a question for the speaker, either write it into the Q&A or at the end you can raise your hand and I will allow you to speak to ask your question. So each of the presenters has 17 minutes and I will give you 2-minute warning. So without further ado, I will ask our first speaker, Ben McKinley, to share his screen.
Okay, thanks, Cath.
Ben is going to tell us about measuring the global redshifted 21 centimetre signal with an interferometer. And that looks good. You can start whenever you'd like, Ben. Thanks.
All right, thanks, Cath. Okay, so yes, we're looking at something a bit different here in terms of measuring the 21 centimetre signal from the early universe. Oh, can't seem to. Sorry, I'm just going to stop sharing.
That's all right, just try again.
Yeah. Okay, it's sharing. Okay, now it's letting me move my slides. Okay, second slide, I just added the moon because I don't like giving talks that don't feature the moon, but have to mostly ignore the moon for this one. So as the first speaker of the EOR session, I guess it's my duty to give you a brief history of the entire universe and the evolution of the 21 centimetre signal. But since this is recorded, and if you're keen enough to be actually dialing in live to the EOR session, I'm going to assume that you know what the EOR is and a bit about the 21 centimetre signal, so I won't go into too much detail. If you're watching the recording and you don't know anything, you can just pause it and go and Google it now. Okay, so welcome back everyone who went away and learned all about the universe. This talk is related to trying to measure the global signal. So we are interested in looking at the average across all of the sky and not all these spatial fluctuations, but just the behavior of the 21 centimetre signal as a function of frequency, which corresponds to redshift. And you can see in one particular model here that there's quite distinctive features in this 21 centimetre signal that in theory we should be able to measure with a fairly simple instrument. How it's normally done is with a single dipole, a well-calibrated dipole. But in this talk, I'm going to be talking about how we might be able to do it with an interferometer. So we've actually published a paper on this recently. And so next time you're writing your introductory paragraph about detecting the global 21 centimetre signal, you can add in Assassin as a new instrument that's trying to do this. And in fact, Assassin only really exists as simulations at the moment, and the real part of it is using the engineering development array, which is at the Murchison Radio Astronomy Observatory, same place as the MWA and ASCAP and future SK low. So I'll talk about the EDA2 in more detail shortly. This is just showing some of the various models that we expect from standard astrophysics for the global 21 centimetre signal. So we're looking at a signal that's somewhere around the 150 millikelvin level and an absorption trough in the signal. But of course, the big news from 2018 was that the EDGES experiment, also out in the Murchison area, detected this really quite unexpected signal, an absorption profile at 78 megahertz that is half a Kelvin in depth and has this sort of flattened shape, which was very unusual, and which we can't explain using standard astrophysics. We need either new physics or to figure out whether, in fact, there's a systematic in the experiment that hasn't been identified. So, of course, we want to verify the edges detection using a different instrument, and preferably one with very different systematics. And so this is what we're attempting to do here. So using interferometer has very different systematics from a single dipole. You should be the signal between antennas that you're correlating, the noise should be uncorrelated, so you should be able to get rid of some of these frequency behavior that is unwanted in a single dipole system. And people don't normally think of an interferometer being sensitive at all to a global signal. You need fluctuations in the sky for a baseline to be able to measure anything interferometrically. But in fact, for very short baselines, there is sensitivity to a global signal. So this is what this plot here is showing. If you have baselines of less than half a wavelength, you have a really strong response here to the global signal. But most interferometers in existence don't have short enough baselines to actually measure this. Fortunately, when I started this project, we realized that we have the engineering development array, which seems like it's sort of ideally built for this project. It's got all these dipoles that have an average spacing of like 1.5 meters, and it operates from 50 megahertz up to around 300 megahertz. So it seems perfect for doing this experiment. We've got lots and lots of short baselines of all different orientations that we can test out. And so that's what we've tried to do using the EDA2 to measure the global signal. So this is the layout of the EDA2. It's got 256 MWA dipoles, and it's laid out in the same configuration as an SKA low station. The dipoles are all orientated either north-south or east-west. So that means your baselines can be between dipoles, somewhere in between these two configurations that are shown in the right-hand panel. So if the unfilled dipoles here show a parallel configuration, and the filled dipoles show an inline configuration, and that affects your response to a global signal. So I've plotted here what we expect the global signal response of the EDA2 to be. And the two lines, the broken line at the bottom and the solid line at the top, they are the two extremes of the parallel configurations and the inline configurations. And you can see the points here that are the expected response of the EDA2 to a global signal fall somewhere in between these two extremes. And you can also see that we have a significant response to a global signal at below half a wavelength. And I haven't actually plotted each of the visibilities here. I've plotted some subset to make it a bit clearer. Otherwise, the whole thing is just sort of full because we have a lot of baselines with 256 antennas. So we've done some simulations to try and figure out what the global signal is going to look like measured with the EDA2. And so on the left, what I've plotted is a simulation where this is just at 70 megahertz and using the edges signal. So it's like a minus 40, a minus 400 millikelvin signal. And in blue is the expected response to a unity 1 Kelvin sky. And the orange is the simulated response of the array to just this minus 400 millikelvin edges signal. And so what we do is we plot the blue becomes the x-axis here, and then we plot the simulated measured visibilities against the expected global response, and you get a line. The gradient of the line gives you this minus 0.4, which is the global signal detected in kelvins. Of course, the line's not going to be perfectly straight when you start adding in noise. We'll talk about that in a minute. So that's what you do. So this was at 70 megahertz that I just showed. So you do that at each frequency channel, and you can recover the signal perfectly when there's no noise and there's no foregrounds, which is pretty good. And then this is just showing the number of baselines used. So we're only using baselines shorter than half a wavelength. And so by the time you get to 110 megahertz here, you've run out of baselines. So what happens if we add a bit of thermal noise? So this is just for a 4-minute observation with the EDA2, and you can still recover the signal in the presence of noise, so long as, well, here the noise is the same as a function of baseline length, which is important. We'll discuss it later. And so if you start putting in foregrounds now, we just put in the GSM foreground. What we found originally, so this is an updated plot from the paper. So in the paper, we found that our subtraction of the angular structure didn't work properly. So what we did is we just simulated the angular structure of the GSM foreground model separately and ran that through the simulations, and then subtracted that from the visibilities. We found that that didn't actually work, and it was because the simulation software we're using wasn't accurate enough. So now I'm using a new simulator from Jack Line et al. Published this year, which was mainly used for simulating the MWA, but he's modified it to do the EDA2 or any antenna array that you want. And it does all of the wide field stuff properly. And so now you can see here that if we ignore the angular response and just plot everything as I did before, you underestimate the size of the global signal and you end up with all these 1.5 Kelvin residuals at the end. But if you subtract the angular structure, you recover the signal and you end up with very small residuals, which is what you would expect for the simulation. And this is just showing what happens when we combine both polarizations. So in the paper, I just used the X polarization. But here I'm just showing that when you combine the two polarizations together, you get a bit better result. The RMS of the residuals from, and these residuals are from subtracting a 5th order polynomial in log-log space. So yeah, you can use both polarizations and you get a better result. But of course, this is not including any effects of mutual coupling. So I expect that someone's going to ask me about the effects of mutual coupling between antennas and the internal noise coupling between the low noise amplifiers in the array. And this is hot off the press. I only just plotted all this stuff yesterday, so I haven't had much of a chance to delve into it and think about it too much. But this is actually including the noise coupling. So Daniel Ng and collaborators published a paper where they simulated, measured the LNA properties of the MWA and the EDA2, and simulated the network response of the LNAs. And this is taking that simulated and measured data and putting it into my simulation so that it includes the effects of internal noise coupling between the LNAs in the array. And the plot on the left is just showing, as before, that when you subtract the angular structure, you can recover the signal properly. And this on the right is the residuals from subtraction of a 5th order polynomial. And the interesting ones are the orange and yellow ones in the middle, from where we've subtracted the angular structure. And what you're left with is these nasty residuals that are still sort of Kelvin up and down, and especially around 70 megahertz there's a nice little trough that's put in by the instrument. And this is stuff that's not going to go away with changing LST or using multiple polarizations or observing for longer. they're baked into the design of the array of the LNAs, etc. So this is, it's not, well, it's a showstopper for the EDA2, but that was kind of expected. The EDA2 was not designed to do this. And so my job was really to design a new array that would be able to do this experiment. So at least now we have a way of simulating and figuring out what the mutual coupling effects are. And so that'll be the next stage, trying to design LNAs and an array layout that allows us to have a smoother response in frequency, especially at this lower end. So we also did verify our simulations using real EDA2 data. So this is an image of the galactic plane. Well, it's the whole sky because we have such a wide field of view. And this is one of those plots at 70 megahertz, I think it is. And you can see this sort of banded structure here is a bit nasty, and that's due to calibration errors, which I won't go into detail now, but you can ask me about it later on. So this is the recovered signal from the EDA2 data. And we end up with residuals of about 7.5, RMS of 7.5 Kelvin, which is dominated by calibration effects and also the unaccounted for angular structure.
2 minutes, thanks, Ben.
Okay, thanks, Cath. So there's just a short note on mutual coupling there. That was there mainly before when I gave the talk a couple of weeks ago and I didn't have the mutual coupling results. So yes, we have a student, Jishnu, who's working on his Sitara project, which is focusing on just 2 antennas to try and verify our understanding of mutual coupling between for a single baseline, and then we'll extend that out to multiple baselines. So this is my conclusion slide, and in fact we've done the top 2 ones there. So we've outlined a new method for extracting global signal from an array of closely spaced antennas. We've used simulations to see what the expected signal is for an ideal instrument and verified this with measurements from the EDA2. So my next job is to work out a way to mitigate the mutual coupling, come up with a better design for a closely spaced array, and also to improve our calibration methods for the EDA2 and subsequent arrays data, and learn more about mutual coupling using the single baseline. So I think I included my own.
Thank you, Ben.
There we go.
Okay, do we have any questions online? Raise your hand if you'd like to speak. We have one question in Q&A from Josh Dillon. I think you can probably read that, Ben, but I'm curious what you're thinking about element and array design that minimizes the effect of mutual coupling without removing sensitivity to the monopole, as was discussed in Venutamov et al. 2015.
Yes, okay. Yeah, I can't see the chat, but anyway, maybe I'll go back to my presentation. Yeah, I don't think we don't want to necessarily remove the mutual coupling because it is closely tied in with the sensitivity to a global signal. So what we want to do is make the internal noise coupling smooth in frequency. So that's what I'll be trying to work on. And as I said, I only just came up with these results yesterday, so I haven't put huge amounts of thought into it. But at least now we have a way of simulating things so we can come up with a better design.
Okay, any final questions? Josh says, thank you, thanks. Excellent, okay, thanks, Ben. I'll clap for you again. Stop sharing, thank you. And we will move to our next speaker. So our next speaker is Saurabh Singh, talking about SARAS-3, a precision radiometer for observations of cosmic dawn. So Saurabh, if you could share your presentation and start whenever you're ready, please.
Hi, can you see my screen?
Yes, looks great. Thank you.
Okay, great. So welcome everyone. I'm SALF-VII, postdoc at McGill, and I would be talking about SALF-III, which is a precision radiometer for cosmic dawn observations. And this work was done mainly at Raman Research Institute, India, across several people in different capacities. So I just get started, and I would thank Ben for giving a very nice introduction already to this field. So yeah, the primary goal of SALF-III is pretty much the same, which is basically to be verifying the origin of the edges signal that's shown here in the blue dotted lines. And just for perspective, the black lines are basically the predictions from the standard cosmology models. So of course, like the detectability of this signal is much better because of its spectral behavior. And SALF-III has been designed, and also the observing environment of SALF-III is different, so that we expect a very different kind of systematics, and therefore the credibility of probing for different origins of this, including whether it's cosmological, is definitely promising. So I'll just walk you through the subsystems and what kind of validation exercises we have done before talking about the deployment. So this is a single element global 21 centimeter experiment targeting cosmic dawn. We have a monopole antenna right as the first element, which is followed by the analog receiver that sits just beneath the antenna. And this is essentially the bandpass calibration scheme along with some amplification. And this is housed just beneath for the reasons that I'll come to later. 150 meters away from this whole unit, we have got the rest of the system that includes the signal conditioning, which is basically filtering out the non-essential part of the band, and followed by a cross correlation to produce the sky spectra. The key point about SALF-III is that it observes on water. And I would really want to focus on why this is important, taking some lessons that we, when we deployed roughly the same instrument on land a year back. So the whole design philosophy of designing these radiometers, at least for SALF, is to be avoiding any spectral structure that can confuse the detection. And we know that in RF system, if we have a particular length scale in the system, there would be reflections, and therefore there would be a ripple corresponding to the periodicity of the length scale that's associated with it. So we have taken lots of precautions to be avoiding that. So one of the reasons for a ground-based experiment is the profile property of the ground or the soil. And if that's the case, then there will be reflections at every profile. And that would basically introduce a lot of fine scale frequency structures. Some of the periodicities could be detrimental to the signal detection. So by going to a different environment, which is water, the first advantage is that it's homogeneous. And therefore, the only length scale here is the distance between the antenna to the lake bed. And we have chosen the sites and the lakes in such a way that any reflections that correspond to that are less than 1 megahertz. So it's not really going to limit us from the signal detection. And the second thing is compared to the ground, in absence of any ground stream, we also have very low efficiency because of the ground losses. While transitioning to the water, that problem is also elevated to a large extent, and I'll come back to that later. So that was the major premise why this very different observing environment has been chosen for this experiment. The next subsystem is analog receiver. And this scheme might be familiar to some of us, which is basically a decay switched radiometer that toggles the noise source on and off. And there is this switch that toggles between the antenna and the noise source to give us the bandpass calibration. We also have a splitting of the chain later down the signal chain, which is at the base station. And what this does is basically creates what we call as the phase switching. And the advantage is that by doing this double differencing, we get rid of a lot of common mode systematics that are introduced later in the chain. Further, these systems are connected by optical link just to make sure that there are no subreflections. And the whole system has been miniaturized to the extent possible so that any reflections that arise because of those length scales correspond to a very smoothly varying signal within our band. And the last part is, of course, we are going to deploy this in remote locations, and therefore this is all powered on batteries and it does not need any main supply. Same holds for the digital system. So this is, as you can see here, it's a cross correlation spectrometer. And it essentially takes the signal here at the ADCs and then cross correlates and Fourier transforms. Also, we want to suppress the interchannel leakage. So we use this minimum photon window that provides us an isolation that's better than 80 dB. And finally, this is one of the most radio frequency generating part of the system. So we also need a very heavy isolation for this. So there is this custom designed shielding that's better than 75 dB. And of course, antenna is 150 meters away. So that just reduces it further. So that was just a quick walk through the system. And I would now switch to what kind of validation exercises we have done before deploying this. So the first exercise is simply replacing the antenna with some of the standard terminations whose impedance properties are known, some of which could be very close to what the antenna should give us. So it's kind of an antenna simulator. And the idea in validating a system performance is making sure that it does not have any wiggles or any ripples within the band. And in order to quantify that, we use this maximally smooth functions. I'll not go into the details of this, but this is essentially a constrained polynomial that does not allow zero crossings in higher orders. So it can fit to smooth part of any given signal, but independent of which order we use, it cannot subtract out any wiggles. So it would preserve all of that. So our main goal is any system response that we have should be modeled by maximally smooth functions just to make sure that the response does not have any embedded structures in them. And we have done these tests in the lab with this receiver and made sure that we go all the way to millikelvin without being obstructed by any systematics. And this has been done actually for both the low band, which is 50 to 100, and also the high band. But I'll be focusing only on the low band, which is 50 to 100 megahertz. Similarly for the antenna, which is more tricky to validate, just because our calibration actually begins after the antenna through this noise source. So there are two different sets of measurements we do to validate this. The first is the total efficiency, which is the transfer function of the sky signal coupling to the receiver. And this is estimated directly from the observation data. This is, of course, important because this is the fraction by which the sky is attenuated. And any imprints of any wiggles or something would get directly translated to our spectra. The other component of antenna, which is trickier, is the reflection efficiency. This is basically the S11 of the antenna. And because this modulates both the internal systematics that are additive and also the sky, which is multiplicative. So we have a very different setup in order to measure this and characterize this more accurately. So this uses VNA and standard loads, switching between them. It's basically another receiver that replaces the actual Ceres receiver right here. And as before, we don't use any coax cables for this measurement and operate everything remotely and then try to compute what the reflection efficiency is. And we have been able to measure that to 5 parts in 10⁻⁶, and we have not found any spectral features that are not modeled by smooth functions. So that basically validates this antenna design. Just to show how this looks like, the red plot here is the reflection efficiency that we measured, and the black line is the total efficiency. So these are the transfer functions for sky and the systematics, basically. And just for comparison, when we deployed this very similar instrument on land, we got the total efficiency that's shown by this black dotted line. So there are two very clear improvements. One, there was this spectral signature, which basically limited us from doing further analysis. And this came from the profile of the ground. So we don't see such a structure when we deploy this on water. And also the actual magnitude of the total efficiency itself increases, so our sensitivity goes up. We don't expect this to be 1, of course, because we have an electrically small antenna. And the reason for choosing such a design is that all these transfer functions are spectrally smooth. So in some way, we are compromising our sensitivity to the sky, but gaining in the spectral smoothness. And we believe that we can always try to compromise because we can enhance our integration time and get to the noise levels that we require. So having done all that, finally, we went for this deployment that happened in 2020. So this was in January and March. And we chose 2 lakes in southern India, both of which conform to our requirements of conductivity, permittivity, also the depth, other things that I talked about. And we observed over some around 10 days. So once we have the data, we have set up this processing pipeline that starts with the raw data that's at 61 kilohertz frequency resolution and 67 milliseconds in temporal resolution. The pipeline basically does 2 important things. The first is the calibration. So using the noise source data does a bandpass calibration, but it also does a very aggressive RFI flagging, which is required because this site is not particularly radio quiet, though much better than other places in surrounding areas. But also the very low-lying RFI, which are fairly broadband, could be the potential limitations, which could either confuse us with the actual signal or they could actually limit us from detecting it. So we have different stages at which we do this RFI flagging in the time frequency window. And finally, we have this average set of spectra for every 30 minutes. Now, in order to choose which part of this we should actually be using for analysis, we compared the RMS of this 30-minute data to what we expect from the simulation data sets. So for each of these 30 minutes data, we generate a set of different noise realizations. Some of them have just the GSM sky and some of them have GSM plus the edges signal too. And we form an expectation of what the RMS distribution should be. So for example, this plot here, the gray histogram shows the distribution that we expect from the simulation data. And then we test it against what we find it in our real data by using some foreground model, which is a log-log polynomial. And we do that at different frequency resolution because if there are some systematics that are very low lying, they get picked up at a much poorer frequency resolution of 1 or 2 megahertz. So the top plot shows how the RMS of the residuals fall when we do different frequency smoothing. That's shown in the white line. And the orange basically shows the magenta and the blue show what we expect from the simulations. So any data set that violates this is rejected because potentially there is RFI or some systematic which may not be useful for analysis. So using this, and again, this is again a very aggressive flagging scheme in some sorts. So we do reject a substantial fraction of this observational data. What we finally end up with is something like 15 hours of data out of the 80 hours that we had observed. And this spans over this LSTs of 10 to 17 that's shown here. Now, in order to test this, we also do a parallel exercise in simulations where we take GSM sky, convolve it with the beam model, basically put in through the same pipeline as we do for the real data. And we can see that applying the same foreground model that we use for the data fits out this to millikelvin levels. So it has at least 2 inferences. The first is our pipeline is fine. And the second is that at least to the known parameter space, we don't have anything that can limit us except of course thermal noise. And also to be noted that this whole observation was done when the ionospheric conditions were really quiet, so less than 15 TCU. And also the wind conditions were quiet, as you can see from this plot. Therefore, a lot of worries about ripples and antenna wobbling and introducing some kind of chromaticity. We have no evidence of that in the data too, just because of the environmental conditions. So this is what we get for the final data. Now, presence of RFI really limits the bandwidth that we can use. So we have finally chosen 55 to 85 megahertz as our band. And we correct this, in addition to the bandpass calibration, we also correct for the additives that are introduced because of the internal reflections of the receiver noise. And also the attenuation of the sky because of the total efficiency, that's of course not 1. So after all those corrections, the top panel shows the average spectrum of those 15 hours. So this is all LST averaged. And the next panel shows the kind of thermal noise that we get. So this is very encouraging because we, even with 15 hours of data, we reach pretty good levels of thermal noise. And also we do not really see any very high ripple, systematic, like what we saw for the ground expedition. So this data seems much more well behaved in some way. And the next panel basically shows the RMS per channel. So this is basically because, of course, the sky brightness temperature varies with frequency, and flagging has another kind of temporal dependence on it. So this basically tells the weights for these residuals. And of course, wherever there is a high flagging, you see these spikes happening. And we normalize using these weights to get the residuals in this units of sigma, along with this distribution. Sorry?
2 minutes.
Okay.
2 minutes left.
So this is basically shown that the data seems well behaved and promising, and we are still waiting for the final outcome of this, and we'll be able to share that as soon as we can. In the last 2 minutes, I'll just switch gears and also talk about a complementary experiment, which is called Pratush. And this is in some way has a lot of heritage of the SARS design, but of course, new set of challenges that come because of this is a space-based experiment. So this is proposed to be in the lunar orbit, observing from the far side of the moon. And it has three distinct advantages compared to the ground-based or water-based experiments, which is shielding of RFI because it's in the far side, all the ionospheric effects, and of course, all the effects of the environment because there is no ground and therefore there are no losses. So this is planned to be observing in 32 to 20 megahertz, and the primary science goal being the cosmic dawn and epoch of reionization through 21 centimeter signals. And currently this is in pre-project mode. So we are kind of designing and revising all our subsystems, and this is funded right now by the Indian Space Agency. So some of the design, so this is again a single system, single antenna system. So we have got antenna, analog receiver, digital that also is interfacing with the satellite bus for communication, data storage, and everything else. So these are just some snapshots of the development activities that we have been undertaking recently. And of course, there are a new set of design challenges that we did not appreciate before. So for example, the presence of the satellite bus near the antenna kind of enhances the metallic structures, and therefore it has a direct impact on the transfer functions. In digital system, we cannot be processing everything on board, so there is a trade-off between what we can store, what we can process and transmit. And of course, everything is compactified together, so therefore it has very enhanced criteria for the electromagnetic shielding. So we are still working on all of these aspects, and hopefully we'll have a final design that is resistant to these challenges. So I would just summarize saying that yes, Session3 has done its first deployment on water, and it's very promising. We have validated the antenna and receiver designs, and we have no evidence of any systematics that limit us. We are still waiting for the final outcome of this. And in parallel, we are also working towards a complementary space probe called Pratush, which of course has distinct advantages over what we do on the ground. I will stop here and take questions.
Thank you, Sarah. I'll clap on behalf of everybody. So we have one question in the Q&A so far. It says, hi, you integrate the spectra for 30 minutes, but after time, does the reduction in RMS noise saturate?
Right, this one I think is being referred to. So the maximum that we go to is 2 megahertz. And the reason is that, as I said, the lake bed to the antenna distance is such that the reflections would be below that. Same holds for any reflections that happen in the optical fiber. So at least till 2 megahertz, we can see that it continues to reduce in a way that we expect, which is basically shown by our noise realizations, because that they don't have any systematics, and they do, the data does follow that trajectory. So we don't see any evidence of saturation at this point.
I think the question might have been integrating for more than 30 minutes, and whether with more temporal integration it continues to go down. Right.
So we have tried all the way. So for this selection, we just restrict ourselves to 30 minutes. So maybe I wouldn't be able to answer that. But of course, the final data is averaged over 15 hours. And that definitely seems to be reducing RMS. It's not saturated. But of course, if we use all of this because of RFI and everything else, at some point would definitely saturate and hit that.
Thank you. And Ravi says, when the RMS noise saturates, you have a detection. Indeed.
Something.
So we have one more question, time for one more from Josh Dillon. He says, great talk. What model is subtracted from your spectrum to get your residual? Is it just a maximally smooth function for foreground removal?
Right. So here the residuals are really not through a foreground subtraction model, but this is just a representation of what the thermal noise should look like. In reality, when we do a foreground subtraction, we use a log-log polynomial to fit out the foregrounds.
Excellent. Well, let's thank Saurabh again, and I will clap on behalf of you. Thank you very much. Thank you for keeping to time. We'll move on to our next speaker, which is Nithyanandan Thagarajan. Nithya is going to be speaking about probing the intergalactic structures and the first quasars in the early universe using low frequency radio observations. So Nithya, I'll just ask you to share your screen and you can start when you are ready.
Do you see the screen?
Yes, we can. Thank you.
Thank you. So my name is Nithya. I work at NIO. I would also like to mention my collaborators on this project, Nissim at NCRA, his student Ajay, and Gianni at INAF. This is work I did because I wanted to take some break from the usual kind of stuff I do, and found it to be quite interesting. There are two parts to this talk. One is to try to probe the intergalactic structures using high redshift quasars as background sources, the 21 centimeter absorption. And the second part, I will talk about probing the first quasars themselves using low frequency radio observations. I won't go into much of an introduction here. Ben and Saurabh have given quite a bit. We are looking at 21 centimeter probes of the cosmic dawn and EOR. As we know, 21 centimeter from H1 is actually a very valuable and robust probe and complementary to Lyman alpha and CMB and other experiments. And generally, broadly, the approach can be classified as the global signal approach, which is shown in the top or the middle panel here, which is to sky average the different types of signals that we see, in this particular case, the brightness temperature. And that's what experiments like EDGES and SARAS and REACH and PRISM, MIST, and any other experiments, including BENS. I'm sorry that I left out so many more that go in here. The other approach would be to look at the spatial structures in the form of fluctuations in the brightness temperature. And one typically takes the power spectrum approach, and a lot of first generation, current generation, and the next generation experiments are going after this, such as LOFAR, HERA, MWA, SK1 earlier the GMRT as well, and paper experiments. Now the fluctuations are typically measured relative to the CMB as a background. Just to keep in mind. So I've been interested in looking at independent approaches, and one of the independent approach that was proposed almost 20 years back by Chris Curley was the 21 centimeter absorption, or the 21 centimeter forest. Just as we are familiar with Lyman alpha forest, where if you have a background quasar and you have intervening gas, the Lyman alpha photons from the background redshifted Lyman alpha photons from the quasar get absorbed by the intervening gas. A similar phenomenon occurs with the 21 centimeter spectral line signal as well. It's just a different spectral line with different probabilities of transition, but otherwise the radiative process is very similar. The radiative process equation I've just written down here at the bottom, where it says that the decrement or the offset that you see from the continuum of the background source depends on the spin temperature, spin temperature and the background temperature S gamma here, which typically could be CMB, but it's also a tunable knob. It could be anywhere between the CMB and anything else that can act as the background source. And if the background source is much brighter than the spin temperature, then it reduces even further to the simple expression where the absorption is directly proportional to the strength of the background source and the optical depth. So this is why it's really an interesting probe, because the absorption strength depends on the background strength of the source and the optical depth. So the stronger the background, the stronger the absorption, the easier it is to see it. And we also require, at these low frequencies, we happen to require high instrument sensitivities. In fact, if you put all these recipe ingredients together, you can figure out a recipe for what is the minimum background strength required, which is shown as this expression S-min. It's typically of order tends to maybe about 100 millijansky for a given signal to noise ratio for the detection. What's the optical depth, other instrument parameters, and observing time. And I should note that many of these parameters here are actually on the very optimistic side. And therefore, even if you see a source of 10 millijansky or 100 millijansky, you are only going to be getting about a marginal detection of signal to noise of 5. In fact, if I went back in the literature and looked at it, I could find about 2 recent examples of a 6.1 quasar and a 5.8 quasar. And if you look at the radio strengths, they're about 50 to 100 millijanskys at about 150 megahertz frequencies. But looking at spectra is extremely hard because we don't have the required sensitivity. So the overarching conclusion is that it's a really interesting experiment, but the prospects are really difficult because it's hard to find a very strong background at these redshifts, a background source, and you require very high instrument sensitivities. So then I started thinking about, could there be a statistical approach to this where you don't have to rely on having a very strong background source. And by having a large number of fainter background sources, could we still get something useful from this approach? And the fact that we also have these large number of background sources, you could also compensate for the sensitivity requirements because you have like large numbers of lines of sight that you could extract extra sensitivity from. The paper by Aaron E.O. Weiss in 2014 actually speculated that there could be a significant contribution from large numbers of not 100 millijansky sources, but more like 1 to 10 millijansky background sources. And if some models of radio quasars at these redshifts, such as by Zoltan, Hyman, and Saxena are to be believed, then they do predict a significant number of such low strength or faint radio quasars at these redshifts. So that's why I thought that there are some interesting possibilities here. So what I started doing was doing a bit of a modeling work where for the reionization model, I took a couple of extreme scenarios, the faint galaxies and the bright galaxies model from Andre Messinger and his collaborators. And these 2 fiducial models supposedly span extreme scenarios of halo masses and virial temperatures. And so they kind of span a whole range of fiducial models that could fall anywhere in between. And here's just a couple of examples shown of what these models look like. The bright galaxies is rather abrupt, and the faint galaxy is a little bit slower transition. One, the onset is earlier, the other one takes longer, etc. But the details of these models are not going to be really important in the subsequent slides. The next model that they included was the source of background radiation. Now, we typically think of quasars, but could be really any radio background, AGNs or GRBs or star-forming radio galaxies, etc. And I've taken an average background strength for these ones, which is either 1 millijansky or 10 millijansky or 100 millijansky. The 1 millijansky representing a faint end, and 100 millijansky representing what I would call as a direct detection of the spectra that I talked about earlier. and a spectral index for these background sources, which is typically a Cygnus-like spectral index of -1.05. And I've put all these ingredients together in the same plot. The left and the right show different fiducial models. You don't have to really pay attention to both at this point. But the red, orange, and green curves show the background source strengths in millijanskis, and then the gray curve shows the CMB strength also in millijanskis. And then the spin temperature of the gas is along a particular line of sight is shown as the fluctuating curve in blue, and the sky averaged signal is shown as the cyan curve. So then I model the instrument. Typically, it includes a array sensitivity parameter, which is denoted by the n times A, which is the effective collecting area of the array divided by the thesis. And I've taken some fiducial models, fiducial numbers for existing arrays and proposed and future arrays. For LOFAR, the GMRT, but an extended version of GMRT that is being proposed, and then the SKA1 low and the final SKA2. I've assumed that the angular resolution in all these studies is about 10 arc seconds, and it's it typically corresponds to about 50, 60 kilometer baselines. And the redshift bands I've considered are around redshift 8, 9.5, and 11. And this is the noise equation that governs how much noise we expect from these arrays based on this array sensitivity parameter. So higher the sensitivity, lower the noise, and vice versa. So the first thing is we put these different things together, the models together, into the radiative transfer equation, and we find that the observed flux densities with the background source and the H1 fluctuations look like in the top panel, but when you subtract off the continuum and then see what is left behind, then you look at what are the offset or the decrement in the bottom panel here. The gray one corresponds to when just the CMB is the background, and then you introduce the other stronger sources, like a 1 millijansky or a 10 millijansky or a 100 millijansky source. And you find that even for the faint source, like the green curve, the amount of signal boost in absorption that you get relative to if you only had the CMB is many orders of magnitude higher. So that can be really exploited. You don't really, maybe you don't really need a 100 millijansky source all the time. You could work with a large number of 1 millijansky sources, for example. And you see that the signal strength also in absorption increases typically with redshift, which is a good sign. And so the requirements are going to become lesser in certain ways at higher redshifts. And yeah, it's unlike when it's just a CMB, you now see the whole thing in absorption predominantly. So before I get into the statistical approach, I should mention that by statistical approach, I really mean a 1D power spectrum. So I take a single line of sight, take the spectrum along that to a background source, and then I take a Fourier transform along that particular line of sight and do this for a whole bunch of different completely independent lines of sights against background objects. So the top panel shows that how you see the signal as a function of the frequency space, which is just the same as the plot I showed earlier, but in narrow window bands or frequency bands. And I apply a frequency tapering window and then take a Fourier transform, and then the power spectrum is nothing but the square of this one-dimensional Fourier transform. I should emphasize it's not three-dimensional, it's a one-dimensional power spectrum. And then what you end up getting at the bottom is these different power spectra, depending on the different strength of the background source. Just if you just focused on any one panel, you will notice that there is a black line which represents the thermal noise component that you expect from a single observation of 10 hours duration on a single background source. And the idea is that you start averaging these power spectra over large numbers of line of sight, and then the thermal noise starts going down incoherently in power. And as it goes down, then you start seeing the signal in power opening up on more and more scales here. The K parallel, the line of sight K parallel scales. And the other thing to notice is that as you go towards higher redshifts, as you skip panels from left to right, you would see that the signal strength is inherently going up because you've assumed the same strength of source, but placed at higher and higher redshift. And so, so one could, for instance, take this picture and invert it and ask the question, okay, if I want to detect a power spectrum on these different scales as a function of scales, as a function of redshift, then what is the required array sensitivity, or what is the number of background objects that I need for this technique to be useful, etc. So that's what I did in the next slide. I asked the question, okay, what's the number of background sources for this power spectrum to actually start revealing a high significance detection? So on the left is the number of background sources, the minimum number required as a function of what scale you want to study. And at low redshifts, you can see that, okay, a saturation at a value of 1 means you at least at the minimum require one source to study. And as you start going towards fainter background sources, you need more number of them, and then that's what is reflected between these red and the orange and green. And as I mentioned before, as you go towards higher redshifts, the requirement on how many objects you need to find and study actually starts going down and becomes less and less stringent. For instance, at a high enough redshift, with about 100 to 1,000 sources of faint 1 millijansky sources, you can actually detect the power spectrum on a pretty wide range of spatial scales. Now, I should also mention that I've assumed that I've assumed certain fiducial parameters. Signal noise required is 5 or greater, SK1 low type sensitivity for the array. The on source time on any single source is about 10 hours, and the angular resolution about 10 arc seconds.
1 minute, thanks, Nithya.
Okay, thank you. So you could also do a similar constraint on what is the array sensitivity required, and we found that the array sensitivity has to be greater than the curves given here. And we find actually that even current arrays like LOFAR and future arrays like EGMRT and SK1 can reveal the power spectrum on a large range of spatial scales here. A similar study was done about what is the constraint on the side lobe quality that we require, because the side lobe confusion is a major source of contamination. And we can, again, derive similar constraints for the side lobe quality of the array that we require for such a study. So the summary is that the 1D line of power spectrum can be actually very useful. It reduces our reliance on extreme sensitivity or a very bright background object, and it reduces the sample variance by sampling a whole different region of the sky. And they can contain significant signal, and even current and future arrays can do pretty well with this. Very quickly, I will just mention that the next part of talk is actually going after these quasars themselves, because studying their properties is very important for understanding the host galaxies and the IgM evolution, their feedback, and how they accumulate their mass so early on in the universe, etc. But some of these studies have been limited by the limited sample size of these high redshift quasars and insufficient sensitivity. So in order to do the study, we've undertaken a massive radio follow-up of optically selected quasars that are at redshifts greater than 6, using the JVLA in L-band and the UGMRT in band 3, which is about 4 or 5 megahertz. We are targeting about 140 to 170 quasars, And we've already got full data from the JVLA and almost complete data from the UG-MART. And these are some of the most sensitive studies undertaken so far. Not the most sensitive, but for these kind of high redshift quasar studies, these are the most sensitive study. And the preliminary results here is, okay, here's a sky map of all the quasars that we've gone after, which is about 170 of them. And the JVLA data we've analyzed so far is about 60 of these fields, and we've seen only about 5 detections at about 4 to 5 sigma significance and 1 detection at 15 sigma significance. And we are routinely achieving noise RMS of about 30 to 40 microjanskeys. So it seems that the optically selected quasars seem to be weak radio emitters. It's not a complete surprise. There's some selection bias, and so this reiterates the need for a radio selection. And in summary, again, I just want to highlight that there is a very large campaign going with the JVLA and the UG-MART going after these high redshift quasars. And we want to understand their accretion modes, their radio loudness, and their evolution with redshift. And there's not been many detections in radio, even with these sensitive data. So the need for a radio-based selection that is not biased by optical selection is kind of needed for, especially if you want to go after these sources as being background sources for such the IGM study that I talked about earlier. Okay, I'll stop there and take questions. Thank you.
Thank you very much, Nithya. That's really interesting stuff. We'll have to move on, and so I'll ask you to respond to the questions that are in the Q&A directly. Okay. So if you could just stop sharing your screen, please. And Shintaro, could I ask you to share your screen, please? Thank you, and unmute, and I'll just introduce you. So our next speaker is Shintaro Yoshiura. He's going to be talking about recent progress of MWA's Cosmic Dawn data analysis. So I'll give you a 2-minute warning, Shintaro, and I'll let you start when you're ready. Thank you.
Sure. Thank you very much. Hi, everyone. I'm Shintaro. I'm a postdoc at the University of Melbourne and Kumamoto University. Today, I would like to talk about recent updates on the MWA ultra-low frequency data analysis. This is a collaboration work with the Dr. Bob Hinder in University of Melbourne and all of your team. So let's move on. Okay, let me start from some motivations. The main topic of this study is the 21 centimeter line from the Cosmic Dawn. So as you may know, the 21 centimeter line is so powerful tool to study cosmology and astrophysics during the EOR and Cosmic Dawn. And ideally, we could measure the 3-dimensional distribution of the IGM during the EOR and the Cosmic Dawn, and also some instruments measure the global signal of the 21 centimeter signal, and we are now attempting to measure that 21 centimeter signal by the radio interferometers. And the main motivation is coming from the EDGES results. As the previous talk mentioned, the EDGES has reported powerful absorption at redshift 18 or something like that. The absorption is too powerful compared to the standard cosmology. So this result have indicated really early star formation and some exotic physics between the dark matter and baryons, and also some paper argued that some existence of radio background before the redshift 18, and of course there's some systematics has claimed. So the follow-up observation of this EDGES results, and it's really important to validate the models. And of course, the follow-up by the global signal instrument is of course important, but the 21 centimeter line, the fluctuation could be another unique observable to validate the edges results. And actually some paper predict really strong fluctuation based on the edges results. And this is one of the example. And this paper have the 10 to the, let's say 10 to the 6 millikelvin squared power spectrum is predicted at redshift 18. So it's really good chance to validate such exotic models by the current radio interferometers. So in this work, we analyzed the MWA phase 1 ultra-raw data for validating the edges results. And the ultra-raw frequency is from the 75 megahertz to 100 megahertz. So redshift range is 13 to 18. So it's overlap with the edges absorption line. And we have analyzed about 15 hours of data to validate the edges result, but it's a little bit the systematics of ultra-raw frequency is quite prominent, and it's difficult to measure the such 21 centimeter signal. So we now aim to obtain the best upper limit at this frequency. And in this talk, I will show some systematics such as the ionosphere and direction-dependent calibration and galactic plane contamination in the power spectrum. And before the calibration, let me show you some RFI situation. So the RFI is usually flagged by the AO flagger in the process for the MWA UR data. And the left panel shows the MWA's typical frequency range. The ultra-raw frequency range is emphasized by the green band here. And you can see the lower side of the ultra-raw frequency overlap with the edges strong absorption. And also, unfortunately, the higher range of the ultra-raw frequency overlap with the FM radio. So it's a little bit contaminated by some RFIs too much, but actually the occupancy of the RFI is pretty clean. And in the light figure, I show the x-axis is the frequency and y-axis shows some mean or median value of the RFI occupancy of the visibility at each channel. And you can see here the lower side of the frequency, that visibility is pretty clean from the RFI. And also you can see some spikes from the FM band. But this data is really good chance to get a better limits for the edges to get better upper limits on the power spectrum at the edges frequency range. So for the calibration, we are using the RTS. So this left figure shows the typical workflow of the RTS. And first of all, the RTS performed a direction independent calibration. So here the gain solution is solved by using the patch sky model and beam model of the MWA. And using the direction independent calibration results, we further performed direction dependent calibration here. And usually we perform the direction dependent calibration for, let's say, a few brightest sources within the field of view, and also perform the ionospheric collection for, let's say, thousands of point sources. And by using the collected gain solution and the collection of the ionosphere effect, we remove some such 1,000 radio sources from the visibility, and we use such residual visibility for further power spectrum calculation. And the one of big issue of the calibration at the frequency is the ionosphere, because the Earth's ionosphere shifts the apparent position of extragalactic sources. And this difference of the position makes the huge residuals after the point source subtraction. So RTS usually perform the collection of the ionosphere by comparing the catalog position of each point sources and apparent position of such sources. And usually this performed for thousands of brighter sources. And using this, the measured ionosphere offset for the 1000 direction, we could reconstruct ionospheric structure using the Kutruf. And this plot shows the 2-minute snapshots of the ionosphere, and you can see the ionospheric structure varies in a few minutes. And actually, we have found some systematics due to the ionosphere. And this plot shows, and this x-axis shows the median offset of ionospheric effect. I mean, it's a median. Oops. Is that okay? Okay. It's a median within of the 1000 direction, and y-axis shows the visibility LMS. And you can see some unknown correlation. They actually, we don't expect any such correlation for the visibility LMS and ionospheric activity. So this indicates some systematics exist here. And we suspect, due to the really large ionospheric effect, the model of the direction independent calibration is not correct. It's not, the sky is not well modeled by the usual, or without the effect, without including the effect of the ionosphere effect. So to improve the direction independent calibration results, we perform the RTS calibration twice. So in the first run, we run the RTS as usual and measure the ionosphere offset for each 1000 point sources. And using the measured ionospheric offset, we update the patchy sky model. I mean, shift the catalog position based on the measured ionosphere, and run the RTS again. And this plot shows the x-axis is a median offset of ionosphere, and the y-axis shows the gain amplitude ratio between the updated calibration and fiducial one. And you can see some correlation between them. And this partially explains the unknown correlation between the LMS visibility and ionosphere activities. So this also indicates the future calibration must include ionosphere effect before the direction independent calibration. And also we would like to optimize the calibration strategy. And this is one of the example, but one of prominent systematics is in the direction dependent calibration. So DD-cal direction dependent calibration is performed to reduce the residual of particularly bright sources. But actually at the ultra frequency, the signal to noise ratio is quite low. So sometimes makes an unwanted spectrum feature after the DD calibration. And the number of source for the full direction dependent calibration is actually a free parameter, and typically 5 sources are chosen, but it's really it's chosen for high band setting, so we have to optimize the number. And as an example, we plot the 2-dimensional power spectrum with the direction-dependent calibration for 5 sources and only 1 brightest sources. And so the left panel shows, oh, sorry, the x-axis is a K perpendicular, which is corresponds to the sky direction, LEDEC, and y-axis shows a K parallel, corresponds to the line of sight, I mean, frequency direction. So, and the color bar shows the power spectrum. And the left one is the result for result with a DD calibration source, a 5 DD calibration source, and middle is for the only one brightest sources. And you can see, and I'm sorry, and the right one is the ratio of them, and you can see here the clear difference between them within the EUR window. So this blue indicates the left one is too bright here in this region, and this also indicates that the error of direction-dependent calibration makes some spectrum feature, and it pollutes the EUR window, unfortunately. So we choose the value of 1 for the fiducial calibration for later sections. Maybe I have more time. Okay. Also, the galactic plane is also a huge issue for the ultra frequency, actually, because the beam of the MWA is really too wide at the ultra frequency, and the galactic plane easily contaminates into the visibility. So this figure shows the model of MWA beam for different pointings and over the frequency diffuse emission of our galaxy. So the solid one is a zenith observation, and dashed and dot dashed line shows that the beam model for off zenith observations. And you can see here, oh, this is I believe this is the beam model for 85 megahertz. And you can see the GP1, this dashed line, this first side lobe completely overlap with the galactic plane. And so GP1 observation should have really strong contamination from the galactic plane. And it's more prominent it's more apparent in the power spectrum regime. And left one is a zenith data, and this one is the power spectrum of the GP1. And this plot shows the ratio, and you can see here the clear contamination from the galactic plane, because the galactic plane is in the horizon, so which exists in the edge of the foreground wedge. But interestingly, the contamination from the galactic plane is not so apparent in the EO window. But so we we include such data in the further integration for now. But presumably, future observation we should remove such pointings to avoid the galactic plane contamination.
2 minutes, thanks, Shintaro.
Thank you. Okay, and also we have two different, we analyzed 2 different EO fields, and the galactic plane contamination is more apparent in the EO0 field. This figure shows the sky response of the MW beam over the galactic diffuse emission and green point sources. And we also analyze EOR1 field. Unfortunately, actually, the galactic plane is luckily in the null region of the beam, but unfortunately, there is two bright sources, such as Fornax and PIK. So the calibration of EOR1 field is a little bit difficult. So it's sometimes make a unwanted spectrum structure after the direction independent calibration. And the difference of these 2 fields is more apparent of course, in the power spectrum regime. So on the left one, this is an example of 10 minutes of data of the zenith observation. And the left one shows the power spectrum of EO0, and the middle one is EO1, and right one is the ratio. And you can see that that means the EOR0 field has a more cleaner EOR window. So this is all the time happen. So maybe it's what makes this diffuse strong contamination strong contamination for the EO1 is not clear, but maybe this is due to the poor calibration due to the bright point sources. And okay, and finally, using the best data set and using the optimized calibration strategy, we perform integration of 3 hours of MWA data for each field and calculate the one-dimensional power spectrum. So I think the left one is the most interesting thing. And here x-axis is a wave number and y-axis is a power spectrum, and different color shows different field of EOR and different polarization. And you can see the red one is for the EOR cell field. This is actually the best power at this frequency range, at this redshift range. It's overlap with the edges result actually. And we got a 10 to the 7 upper limits. And I think the 2 sigma upper limit will be 2 times 10 to the 7 or something like that. But it's about 1 order of magnitude better than previous analysis actually. So it's really encourage us further processing will improve this upper limit and will validate the edges result. And there's, of course, we have to reduce more 1 or 2 orders of magnitude. We have to reduce the upper limit 1 or 2 order of magnitude to validate the edges result, but it's kind of encourage and promising result, we think. Okay, as a summary, we have analyzed the MWA ultra-raw data, which in order to validate edges results, and we could get a better upper limits compared to previous work. So we think the future observations such as MW phase 3, SK1 low will break this upper limit easily. And we have found some systematics such as the ionospheric contamination and the galactic plane and direction-dependent calibration make some unwanted spectrum structure. So we, as a remark, we suggest for future data analysis to include ionospheric model in the direction-independent calibration and perform the direction-dependent calibration for really only two light sources to keep the high signal to noise ratio. And of course, we have to take care about far side lobe contamination to avoid a galactic plane. Okay, I think that's it. Thank you very much for your time.
Thank you, Shintaro. I think we have time for just one question. Brina Hazelton has one in the Q&A. She asks, you mentioned that you use only one source for the direction-dependent calibration because of the spectral errors. Is that for the first loop or the second loop through the full calibration?
It's for both. I mean, actually, that direction. Okay, I'm reading the question. Okay, yeah, okay. It's for the second loop through the full calibration.
Excellent. Thank you very much. So I will thank Shintaro again on behalf of everyone, and we'll move on. Shintaro, can you just stop sharing your screen? And we'll move on to our next talk, which is Nicole Barry. I'll ask her to share her screen. So we have Nicole Barry from the University of Melbourne, the MWA cross-pipeline study, observational versus analysis systematics. Start whenever you're ready. Thanks, Nicole.
Thanks, Cath. Yeah, so my name is Nicole Barry, and I work on Epoch of Reionisation observational science. And I'm a postdoctoral researcher at the University of Melbourne. And so I work on the Murchison Wide Field Array. And today I want to do a cross-pipeline study to try to find clues about where our systematics lie. You can fit the early universe onto a very simple timeline, which starts with the Big Bang and goes through the Dark Ages for about 500 million years. There's just primordial neutral hydrogen with a sprinkling of other stuff floating about. And then over the course of time, this coalesces under the force of gravity into the first stars and galaxies, which then kicks off the Epoch of Reionisation, which is really the final time period before the modern universe. And it kind of marks this transitional period, almost the last phase change before we really get into modern day astrophysical universe. And the Epoch of Reionisation may have looked something like this. This is a simulation from the Dragons team, Paul Gale and Simon Much in particular. And you have your neutral hydrogen here in red. Over the course of time, as the first stars and galaxies turn on, they rip apart the neutral hydrogen, rip apart the proton from the electron. And neutral hydrogen has a special property. It releases light at 21 centimeters. That's the hyperfine transition. And so if we look back in time to try to measure this 21 centimeter signal, hopefully we can actually see these really complex structures over the course of time, ending at about a redshift 6 or so. And if we were able to do that, we might learn a lot about various cosmological and astrophysical parameters that we can't really constrain at the moment. So this is a cute little GIF from Greg Park and Messinger as well. And I don't really want to go into each of the parameters here, but this is just to try to show that there is quite a range of parameters that you can constrain by looking at the Epoch of Reionisation. And different Epoch of Reionisation realizations result in different parameters. And so that's really the goal behind, the scientific goal behind trying to measure this 21 centimeter signal. But it's difficult, and that's because there's a lot of stuff between us and the Epoch of Reionisation in the early universe. And since the 21 centimeter signal is redshifted into the radio frequencies by the time it gets to Earth, you are in contention with everything else at those frequencies. In particular, this includes galactic foregrounds, stuff from our own galaxy like synchrotron emission, supernova remnants, and extragalactic foregrounds, basically all the other radio galaxies out there. And you can actually visualize this as slices in the universe, and using some statistical methods, we can actually collapse these slices into one bin. And that's because even though the gas in nearby galaxies, including our own, is 5 orders of magnitude brighter than the EOR signal we're looking for, it has a smooth spectrum in comparison, whereas the 21 centimeter signal varies quickly as a function of frequency. And so you can take a Fourier transform to collapse your foregrounds. So I'll be showing 1D power spectra today, 3D Fourier space binned down into 1D. And so if you have, say, bubbles on the sky, bubbles and structure in your Epoch of Reionisation signal, the larger ones will be towards the left side of the plot, and these smaller ones will be towards the right side of the plot. And the x-axis really just kind of traces out distributions of these cosmological structures. And the more sizes of a particular bubble you have, the more power you will have in that particular K-mode. And so this is our theoretical hope when we built the instruments, that we would take Fourier transforms of the signal that we received and collapse all the foregrounds into the very first bin, thereby leaving all of these other modes in which to measure the Epoch of Reionisation in. But that didn't happen because the instruments themselves have a chromatic response. They have a response as a function of frequency. And so that response actually bleeds the foregrounds out into many more modes, which then destroys those modes, essentially, for trying to measure the Epoch of Reionisation. However, there's still quite a few modes in which to go looking. So that's what we currently are doing at the Murchison Wide Field Array. But then let's say you have an analysis and you make some errors. It's a very valid assumption here. And let's say those errors are 1 part in 10 to the 3 as a function of frequency. The power spectrum you might measure might look something like this, where all of the modes that can be described by the spectral errors you've made are now fully contaminated because your foregrounds were so bright to begin with, they have now bled outwards. And so really the name of the game, an epoch of reionization science at the moment, is to reduce these errors, whether these errors are due to analysis systematics or observational systematics. And the analysis is quite a, there's a lot of moving parts, a lot of modules. It's not unheard of to think that there might be errors creeping in a variety of these different analysis procedures. This is just a very typical analysis that you might see for the EOR. You start off removing R5. You then go into some calibration procedures, direction independent and direction dependent. You then can remove some foregrounds, typically point sources. You then do a gridding step, which is basically just a fancy term for histogramming all of your measurements onto the same plane. You can then do some imaging, and you can remove some diffuse foregrounds in those images. And then finally, you make power spectra. And we wrote a paper last year on the pipeline that I typically work on. It's a very straightforward pipeline, I would say, though I am biased. So if you're interested in the different procedures that go into something like an EOR measurement, you can check that out. And there's this unique situation that kind of happened when we were building epoch of reionization pipelines for the MWA. You have a pipeline that was built in the United States mostly, and a pipeline that was built in Australia mostly. They are independent, but they were built at roughly the same time. And so what we want to do is we want to take the outputs from roughly halfway through each of the pipelines and plug it into the other pipeline. So in this example, it would be taking outputs from FHD, plugging it into chips, taking outputs from the RTS, and plugging it into epsilon. And so the idea here is to really just switch the modules to try to make a new pipeline in which to investigate systematics. And this has been done before. So this was done in 2016 on 3 hours of data, which is a very small sample. And the idea behind this was really validation. We wanted to make sure that, that we got within an order of magnitude. And we learned things like our polarization conventions were different. We validated calibration or cable reflections coming through in the pipelines. And again, once we got to an order of magnitude, we basically stopped because that took 3 years of effort. And that was really broad strokes, the lessons that we learned in 2016. But now it's 2020 and things have matured quite a bit. And so we want to do a similar process, but with a limit quantity of data. And what we're really probing here is trying to suss out differences between analysis systematics and observational systematics. And I'll walk through an example here in a second. But I'll draw your attention to the little matrix on the right. So I have a color-coded scheme to try to make it easy to analyze these results. So things that are green went through FHD, things that are blue went through the RTS, things that are dark went through epsilon, and things that are light went through chips. And so for analysis systematics, logically, most likely analysis systematics will manifest in only tests with that analysis. So for example, let's say FHD had a calibration systematic. Then the results that I get that were green, that the top line in this matrix here, would have higher systematics than the blue. Conversely, for observational systematics, most likely they'll manifest in all of the tests, regardless of the analysis used. So that's dependent on the fact that, let's say you have an input where something in the instrument caused a systematic. You would expect to see it in all 4 of the cross pipelines that we're doing. And of course, these lines blur, so it could be an observational systematic that wasn't properly handled in analysis, and so you might see not quite this simplified example. However, these are clues, right? These are clues which direct us to go looking for one or the other. And so this is what a limit quantity amount of data looks like going through the American pipeline, shown here in green. And this is the same data set that was used for Berry et al. 2019b. You have 2 lines here. You have the solid line, which is the actual upper limit, and you have the dashed line, which is a thermal noise line, which kind of just quantifies how deep you can expect to go with that particular data set. And if I now plot all 4 of the tests that were done using the same exact data, you can see that there are some coherent structures between each 4 of the tests. And I'm going to walk through a couple. But I do want to point out that there are these large harmonics happening. This is a known systematic. Those are the coarse band harmonics caused by requiring some regular flagging due to aliasing in our polyphase filter banks. So those are known, just so you know. All right, the first thing I can see here is that the RTS, things that are blue, have a higher systematic floor than things that are green. And to me, that says that there's something in the RTS which has higher systematics compared to FHD. And so some of the fantastic work that Shintaro has been doing indicate that perhaps this is direction-dependent calibration. So that's something to follow up on in the future. Another thing that I can immediately see here is the darker colors, things that went through epsilon. If you look at the coarse band harmonics, these are higher than the things that went through chips, the lighter colors. And so that indicates that chips is doing something better than epsilon when it comes to the coarse band harmonics. And I don't think either of these 2 things I pointed out are really big surprises at the moment. However, they are good to see in this space, things that we somewhat expect as things to chase up in the analysis. So now what I want to try to think about is, what about observational systematics, things that perhaps we didn't know existed. Just to highlight again, those are coarse band harmonics, those are known. There's also a cable reflection right here, 150-meter cable reflection. That's known as well. But I'm just going to flip through a variety of different slices of the data. So I've split it up into 5 different quantities of that data set. And if I plot them all, I'm trying to look for coherent structures here. I'm trying to see, are there any bumps on anything that's standing out? And here I've plotted all 5 of those slices together just to try to see by eye if anything is coming out. And
thanks, Nicole.
Thanks, Cath. I'm focusing on this region here because this is where we're most sensitive. I can almost see a bump. Can you? And I can almost kind of sort of see bumps in between the coarse band harmonics, kind of like a double cadence. But maybe this is not the best of analyses to do. A by-eye assessment can lead to conspiracy theories. So what I want to try to do is get a statistic that shows that there is some sort of double feature. This is an autocorrelation of those signals. And so really quickly, if I direct you to my video, if you have a signal, the same signal, when it's right on top of each other, lag of 0, it's perfectly correlated. So it has a correlation of 1. And as I lag 1 compared to the other, as soon as features line up again, I have a correlation. However, some of my fingers are longer than others, so it's not a perfect correlation. So that's what's happening here. Your coarse band harmonics are roughly 0.4 h megaparsecs away from each other. So that's what that feature is. And you can see some weak correlation evidence for a double feature between the coarse band harmonics, which doesn't appear to be very strongly correlated at all for the American pipeline, the dark green. If I run through the slices again, you can kind of see that this is a persistent feature. It doesn't really seem to depend on the slices of data that I've taken. And so this kind of raises the question, well, what is going bump of the night then, which appears out of 3 out of the 4 pipelines that we've done. Is it an observational systematic? Most likely. Could be analysis though. And at this point, I'm just trying to get people's thoughts and theories really about what they think this could be. I have my own theories and I'm pursuing them in simulation to try to validate them, but at the moment, nothing has been confirmed. So I'm open to your thoughts on the Slack channel. I hope to see you there. And if not, you can look for the paper coming out this year. And just to wrap up, this is great and all, but I think there is a real opportunity here to open up these degrees of freedom to include LOFAR built pipelines. Obviously, this will be harder to incorporate cross-pipeline analysis between pipelines that are done for different instruments, but the potential, the discovery potential with this type of analysis is great. And so even further in the future, I want to be able to do something like this, where I take individual modules from the 3 pipelines and I switch them out for just to test things and to see what happens. So in summary, the EOR is a good place to look and we can learn a lot from it, but the analysis needs to be extremely spectrally precise. And so a cross-pipeline analysis can really access more degrees of freedom and is an extreme robust validation procedure in try to determining normalization. And there's a lot of potential for cross-collaboration studies in the future. So I'll stop there and take questions.
Thank you, Nicole. We have a question pop up right now from Josh Dillon. Nice talk. Love the graphical representation of the pipeline steps. Yes, I agree with that. Why does the thermal noise level vary between the pipeline combinations? Great question.
Oh, Josh. Okay. Yeah, so that's a really good point. And just to bring it up, what he's talking about. So you can see some variation here in the thermal noise. Obviously, these are different sets of data, which are not completely the same between the 5 slices that I've taken. However, when you're comparing the different pipelines together, their thermal noises are slightly different. Partly due to the fact that some systematics can creep into the thermal noise. And so we've actually seen that with the American pipeline. Actually, things that go through Epsilon in general have to go to image space. And that the subset of systematics that come in when you go to image space can actually affect the thermal noise prediction that you've made from those, from the variances that you have in the image. And so we actually know that things that go through the American pipeline are roughly a factor of 2 too high, but that's an estimate. So there's something there. There's also this question about what you thought the sky temperature was to begin with. And some of the pipelines, some of the packages have different assumptions. I've tried my best to try to constrain those individual assumptions to be the same, but obviously perhaps not perfectly. Really good question.
Thanks, Nicole, and thanks, Josh, for the question. So I thank Nicole again I'll clap. And just a reminder that we have a virtual coffee after this session, and that's a regular Zoom where people can discuss. And so anyone can discuss with Nicole their thoughts on those different systematics and the lag correlations there. So we're going to move to our final speaker of the session, and that's Mahsa Rahimi. So Mahsa is from the University of Melbourne, and she's going to speak about new MWA Epoch of Reionisation power spectrum measurements of the EOR1 field. So I'll ask you to share your screen and start whenever you're ready. Thanks, Mahsa.
Okay. Hi, everyone. My name is Mahsa Rahimi. I'm a PhD student at University of Melbourne and working with MWA EOR group. Today, I want to share with you the results of my research on observational study of epoch of reionization. As the other previous talks introduced the science of EOR signal detection, we are dealing with a very faint signal at the epoch of reionization, which is mainly focused at redshifts of 6 to 8. And so the main characters that play roles in this scenario are the foreground, the ionosphere, the calibration, and the RFI that we need to manage them to get a better results for EOR detection. The instrument that in this project uses is the MWA, which is a radio interferometer that is located in a radio quiet zone, and I am using the configuration of phase 1 of MWA in this work, and the frequency band is 167 to 197 megahertz. And I'm looking at the data observed at 2015, and the target field of my study is EOR1. And this is the configuration of the phase 1 of MWA. And as you can see, it has a compact core and the other antennas extend out to the radius of 1.5 kilometer for better resolution and calibration. The analysis pipeline that I'm using at this work are RTS, or real-time system, that is for calibration and peeling. It performs the calibration in a two-stage process. First is the calibration, which uses a single compound calibrator that is made of 1,000 brightest sources of the field, and then goes for the peeling of the foreground sources. First, it performs the direction-dependent calibration for the brightest sources of the field, and then does the ionospheric correction on amplitude and phase of the sources, and then the foreground sources are peeled. Then the calibrated visibilities are fed into chips, which is the cosmological H1 power estimator. It directly computes the power spectrum from the calibrated visibilities and employs an inverse variance weighting of the data through maximum likelihood estimator. The main focus of MWA EOR study is on three fields: EOR0, EOR1, and EOR2. As you can see, they are selected in almost cold regions of the sky, and EOR0 and EOR1 transit at zenith at the location of MWA. And this study processes the data from EOR1 field. The previous EOR study that has been done by Trott et al. 2020, they have computed deep multi-redshift EOR measurements from these three fields, and they had computed the upper limit of 43 millikelvin for 110 hours of integration time from EOR0 field. Also EOR2 had compatible limits, but EOR1 had the very poor results out of 600 observations. So we are looking at how we can improve our processing for this field. Okay, EOR1 field, as you saw in the global sky map, is in a cold patch of the sky, but it contains the bright radio galaxy of Fornax A, which is several hundred Janskis bright, and it is a very extended source and has a spectral distribution. So we need, at the first step, we needed to improve our source catalog. The initial source catalog was based on Gleam catalog and cross-matched with Puma to use the other catalog sources. And the shapelet model has been used for modeling Fornax. And also the high resolution images of the GSS were used for modeling extended sources within 10 degrees of the field center. At the next version of the catalog, the extended models were also applied to other sources of the field. So this has been improved for all of the sources. And in the next version of the source catalog, we also improved the shapelet model of the Fornax, and it was based on the MWA phase 1 and phase 2 image of Fornax. The other point that I would like to mention that are important for this work is a comparison of 2015 and 2013 data, and it is due to the record of dead dipoles in the data. The 2015 data have the record of the dead dipoles. So the beam profile and the weighting of the data are adjusted according to the available dipoles, but this isn't the case with 2013 data. This is confirmed with these plots, which is the visibility RMS noise of data for 2013 and 15. So you can see that the 2015 data has lower RMS noise, if we disable the dipole flagging in 2015 data to simulate the case with 2013 data, we get the same RMS noise. So that is making difference for data sets that include 2013 or not. And it is also confirmed with the power spectrum. As you can see, this is the 1D power spectrum for 2013 in blue, which is the higher, and 2015 in orange. And if I disable the dipole flagging, the power spectrum gets higher. So this is another point of 2015 data. I have here summarized the effect of all of the improvements here. The 4 higher power spectra are with the first version of the source catalog. The blue and the orange one are higher due to a numerical issue with the peeling, that after they have been resolved, the power spectrum gets lower to the red one. And again, to confirm the dipole record in the data, if we disable them, they will get higher as a green one. The purple one is the power spectrum with the second version of the source catalog, that the extended models were applied for all of the sources of the field. And the brown one is the power spectrum of the last version of the source catalog with improved shapelet model of the Fornax that is used in this work. Now, if we want to look at more closely at the differences between EOR0 and EOR1 field, you can see here that it is a whole sky map of EOR0 in high band, and the EOR0 has the contamination from galactic plane, while the EOR1 has Fornax A in its primary beam. To compare the sky temperature of these two fields, we use the GSM model prediction to estimate the sky temperature for these two fields. As you can see, the EOR0 has higher temperature due to more diffuse emission. And also this is confirmed observationally by driving the system temperature from visibility noise RMS for EOR0 and EOR1. EOR1 has lower system temperature. To look at the data, the available data in more perspectives and understand more about the data, we try to look at the data for different nights and different pointings for different fields to see if there is any correlation between these different aspects of the data. The top panel is for EOR1, the bottom panel is for EOR0. The first column is shows the RMS profile. The middle one shows the ionospheric activity, and the last one is the Bondi power spectrum, and they are coded by the pointing. The second and fourth row show a typical night that have very smooth profiles with RMS and also with ionospheric activity, but the first and third row show another night that has typically more noisy RMS and ionospheric quantity. We wanted to see all of these features in 2 typical nights. So as you can see, there is a decrease trend for RMS over the LSD for different pointings, but it is not something that is predictable in all of nights and also with the ionosphere. And also we couldn't see any correlation between the Bondi power spectrum of different observations per pointing. The main interesting finding of this work is the comparison of EOR1 and EOR0 power spectrum. As you can see here, the 2D plot, this one shows the EOR1 to EOR0 ratio and EOR1, the difference of EOR1 and EOR0. The blue one means that EOR1 has higher power. And in the ratio one, you can see that this diagonal signature along the horizon, which is coming from the galactic plane diffusion in EOR0 that is making this difference for EOR1 and EOR0 difference. And so we expect to see lower power for smaller wave numbers or larger scale that is confirmed by Bondi power. EOR1 has generally more power than EOR0, but for at smallest wave numbers, it's cut by the Bondi power. So galactic plane plays an important role in this comparison. We also have applied data quality metrics, very curious, cautious data quality metrics to filter the data. For example, we first of all, we looked at autocorrelation. As you can see here, this is the autocorrelation of 10 typical observations. And this is a variance of autocorrelation over frequency. We could see some features like the digital TV or other systematics in the autocorrelations, but at this point, they were not, their effect was not detectable in the power spectrum. Maybe future, if we get more sensitive power spectrum, we can detect them. And also we looked at calibration-based metrics such as ionospheric quality metric, calibration solution, and also visibility noise RMS. Then we go for window and wedge power metric, individual power spectrum, and at the end, ultrafine RFI and calibration filtering, which is using SINs that plus the noise spectrum of the visibilities. As you can see here, you can see digital TV in this observation. And so at the end, we could cautiously select 463 observations, which is equal to 14 hours of data. And also we wanted to look at the visibility noise RMS metric more closely, and because we noticed that there are some, there is a clustering between the RMS values of observations. So we try to look if this is making an impact in the power spectrum and due to systematic in this kind of observations. So we group them into low RMS and high RMS observations. And as you can see, there is a significant difference in the power of these two groups. And they are analyzed with the same number of data observations. And also we looked at the, here we look at the power spectrum difference and ratio of these two data sets. As you can see, the red means that the low RMS is low, it has lower power. And here the boundary power also confirms this finding. Here I am, yes.
Sorry, 2 minutes, thank you.
Thanks, Cath. Yeah, and here I have compared the only low RMS observation with a mixture of low RMS and high RMS data set. So it's a point that we can take into account when we are dealing with, we want to have a very clean data set. And at the end, this is the primarily upper limits of the 463 observations. And as you can see, for the for these three redshifts, we get the lowest upper limit of 80 millikelvin at redshift of 6.5, which is now comparable to the results of the other fields. And also because of the potential of the EOR1 field that doesn't have the galactic contamination, it's very promising that we can get a better result with even more integration time, because it was just with 14 hours of integration time, but with the compatible results. Here I left my summary, and this research was an effort to improve the power spectrum measurements by improving the source catalog and source modeling, and also having strict data quality metrics. Thank you.
Thank you, Masa. Excellent. So we have one question in the Q&A so far, and it's from Brenna Hazelton. By dead dipole flagging, do you mean that you are using a different beam per tile that reflects the dead dipoles, or do you mean that you are flagging tiles with dead dipoles?
The dipole flagging disabled, I mean that because the 2015 data didn't have, has this information, the beam profile and the weightings are adjusted to accordingly, but because this information is not available in 2013, so we couldn't do this adjustment, so it introduces noise to the data. So by disabling this feature in 2015 data, I am just simulating the condition in 2013. I hope this answers your question.
So Brenna follows up by saying, so are you adjusting the beams?
Yes.
Okay, great, thank you. Do we have any final questions for Masa? No, in that case, I'm going to thank on behalf of everyone, Masa and all the other speakers of this session. Just as a reminder, the talks from yesterday's session are all available on the YouTube channel, and Jason Hessel's put the link to that in the chat. And now if you'd like to get your beverage of choice, depending on where you are in the world, we'll move to the other Zoom for a coffee, tea, drink break, and I put the link to that also in the chat if you'd like to join for the next half an hour or so, and that's a regular Zoom, so everyone will be able to chat. Otherwise, the next science session begins in 6 hours at 0900 UTC, and we will see you all then. Thank you and goodbye.